So our last integration-related topic of the semester concerns so-called improper integrals. So when we were looking at finding the area of some planar region, the region is always bounded. It's always finite. It's bounded by some collection of curves. So we consider now the question of finding the area of an unbounded region, a region which is infinite. Now, at first, you might think that it's a silly question, because if the region is infinite, then surely it's going to have infinite area. But, as it happens, this isn't really the case. We have to think about this a little bit more precisely. And the ultimate application of this sort of thing is going to be not just in talking about infinite areas, because that's really just an analogy. I mean, remember, the units of an integral depend on the units of the function that you're feeding into it. So, ultimately, this idea is going to have applicability everywhere in science and mathematics, not just in computing areas. But we like to think about definite integrals as computing areas because it's easy to put a picture in your mind about what's going on conceptually. But, yeah, what we're doing here is, of course, much more far-reaching than that. So, the definite integral can compute the areas of bounded regions. That is the case by definition. What we can do then, to possibly extend that to unbounded regions, is to take a limit. So in particular, consider the region below the graph 1 over x squared. So this guy has an asymptote at x, but then it just decays towards 0 as you go out to infinity. I would bring up GeoGebra right now, but my internet's dead. Like, completely dead. So, that's fun. I'll have to upload this on campus, I think. Or maybe I'll go to McDonald's and use some of that famous McDonald's internet. So what we can do is we can take a definite integral, say the integral from 1 to t, where t is just some number, and we can certainly compute this. And then let's just take the limit as t goes to infinity. And what we will effectively be doing then is finding the area of the unbounded region, albeit as a limit. So, indeed, this is easy enough to compute. We can just hit this guy with the power rule to get that. Plug in t and 1 and we get that. So this is the area of the region under this curve between x equals 1 and x equals t. And then as t moves farther and farther and farther to the right on the x-axis, this area approaches a limit. Namely, it approaches a limit of 1. So it is reasonable then to define the area of that unbounded region as being equal to 1, because it's completely consistent with the notion of area that we have been working with. So, we can abbreviate this limit up ahead as being an integral from 1 to infinity. So it's as if we are integrating this integral over an infinite interval, right? The interval from 1 to positive infinity. And indeed, this is how we're going to interpret this symbol moving forward. So when there is an infinity in the upper limit of an integral, really all that means is that we are replacing this with some parameter, call it t, and then take the limit as t approaches infinity. So we're going to call this an improper integral of type 1. An improper integral of type 1 is one that has infinity in one of the limits of integration. And then, of course, there's going to be a type 2 later, which is slightly different. So if there's an infinity here, replace it with a parameter, and then let t approach infinity. If there's an infinity down here, well, same story. Replace that infinity with a parameter, and then let that parameter approach negative infinity. Now, if the integral... Whoops, this should be an a here. So, if the integral with upper limit infinity and lower limit infinity exist, then they are called convergent. Oh, whoops, I was wrong. This should be B, because this line is just introducing the notation convergence. Yeah, so if this limit exists, we say the integral is convergent. If the limit doesn't exist, we say the limit is divergent. Yeah. Now, if the integral with upper limit infinity and negative limit infinity both exist, they're both convergent, then we define the limit, or the integral with infinity in both of its limits, to just be the sum of those two one-sided improper integrals. So that is the case by definition. Okay. So really, we're not introducing too much new in this section. I mean, computing an improper integral is literally just computing an integral and then taking a limit. That's all there is to it. It's just two processes, or, you know, two types of exercise that are now coming one after the other. Okay, so this dude here, by definition, this is the limit as t goes to infinity of the integral from 1 to t 1 over x dx. So literally just replace the infinity with a parameter and then take the limit as that parameter tends to infinity. So here's what I'm going to do. I'm going to copy this symbol to my clipboard because I'm going to be using this guy a lot. Okay, what's the antiderivative of 1 over x? Well, that's natural log. And that is evaluated between t and 1. So that is natural log at t. The absolute values aren't required because t is larger than 1, and so it's positive. Minus natural log at 1. Well, natural log at 1 is just 0, so all we're doing is we're looking at the limit as t goes to infinity of the natural log of t. And the natural log explodes. The natural log explodes. So this improper integral is equal to positive infinity. In other words, the limit doesn't exist. So this guy is divergent. So, notice that when we did our first example up here, integral of 1 over x squared, we got a convergent integral. It ended up being 1. Whereas when we are integrating 1 over x, the only difference being that there is no square here, it ended up being divergent. So a common mistake that I have seen is for people to just assume that because the integrand is tending to 0, then the improper integral must exist. But here is a clear counterexample of that. 1 over x and 1 over x squared are both going to 0 as x goes to infinity, but when you attempt to take the area under the curve, well, this guy has unbounded area, whereas this guy has bounded area. So, yeah, so you do have to compute the integral in this case. Okay, let's evaluate this dude. So this is the limit as t goes to negative infinity of the integral from t to 0, right? So just replace the problematic aspect with a parameter and then take the limit. Now, how can we attack this dude? Let's do integration by parts on this. Right, it's a product of elementary functions, so integration by parts should work. X is an algebraic function, so that should be our u, which means du is just going to be dx. Dv has to be everything else, so that's e to the x dx, which means that v is the antiderivative of this thing, so that's just e to the x. So now if we plug this into the integration by parts formula, let's see. So it's uv, so x e to the x, minus integral v du. Like so. And because this is a definite integral, we have to keep the bounds in mind as well. Okay. So for this first guy, if we plug in the bounds, so 0, well, that all becomes 0. Minus t e to the t minus antiderivative of e to the x becomes e to the x. And that is evaluated between 0 and t. So let's see, if we plug in 0, we get e to the 0, which is 1. If we plug in t, we get e to the t. And then this minus sign has to distribute, right? Because this is 1 minus e to the t, and then I flip the signs there because of this minus. So, got to be a little careful with that. Okay, so what happens as t goes to negative infinity of these dudes? Well, e to the negative infinity is 0. 1 is just 1. What about this guy, though? Because e to the negative infinity is 0, but if we put a negative infinity here, we get infinity. So this is infinity times 0. Well, that's an indeterminate form. So we're going to have to rewrite this to use L'Hopital's rule somehow. So let me just point out. So this dude becomes 0, this dude becomes negative 1. So there we go. Alright, so let's rewrite this to use L'Hopital's rule. So the latter limit is of the form infinity times 0, so we need to rewrite this as a fraction. So let's see, let's write this as, so we did an example that was almost exactly like this in the previous section on L'Hopital's rule. So we can write that. And now we get, yeah, so now we get infinity over infinity, right? Because negative infinity is positive infinity, so yeah. So infinity over infinity means we can use L'Hopital's rule. So the derivative of t is 1, the derivative of e to the negative t is negative e to the negative t. So minus minus becomes plus. One over e to the negative t is just e to the t. Okay, and as t goes to negative infinity, this becomes 0. So there we go. So our final answer is negative 1. A lot of work to get that out, but, you know, each individual step is a thing that we have seen before, right? Each individual step is a type of exercise which we, at this point, should have a lot of practice with. So we would say that the integral is convergent because because it exists and equals negative 1. All right. So now let's evaluate this dude. So here we have negative infinity and positive infinity in the limits. So by definition, we have to split this into two pieces. And we can pick the middle piece to be whatever we want. So let's just pick it to be 0. That's easy enough. So yeah, I could have picked this point to be anything I want, but I picked a 0 for convenience. Okay, so we're gonna have to compute both of these. But since this is an even function, these are actually gonna both end up being exactly the same, if it exists in the first place. So let's focus on just this one on the right. So this is the limit as t goes to infinity of the integral from 0 to t, right? Just replacing infinity with a parameter, 1 over 1 plus x squared. Now, what's the antiderivative of 1 over 1 plus x squared? Well, that's just the arctangent. So this one is given to us for free, so to speak. Yeah. And that's evaluated between 0 and t. So arctan at t minus arctan at 0. Well, let's see. Arctan at 0 is 0, right? What angle gives us a tangent of 0? 0 does. So this is yeah. So that second term just doesn't even need to be there. And then what is the limit of the arctangent as t goes to infinity? That's pi over 2. Right? Go back to our section on inverse trig functions. This is one of the facts that we brought up. Okay, so yeah, this guy converges. And because this is an even function, I mean, this is exactly the same. I'm just plugging in negative numbers instead of positive numbers, but those negatives are just going to be squared away. So yeah, this and this are exactly the same. So since 1 over 1 plus x squared is an even function, we have that this is going to equal pi over 2 as well. Yeah, because it's going to be arctan of 0 minus arctan of t as t goes to negative infinity. So that's going to be negative pi over 2, which is positive pi over 2. So yeah, work it out yourself if you want, but it follows from the fact that this is even. So, to get the final answer, we just add those two guys together. So it's pi. So that's kind of impressive. That's kind of interesting, right? You wouldn't necessarily expect for a constant as universally beloved and ubiquitous as pi to pop out of something like this. But, well, here you go. In fact, I remember seeing a bumper sticker once where the bumper sticker just read, "If you can evaluate this integral, then you're driving too close," or something like that. So yeah, it took me a moment, but yeah, I got in my head, oh yeah, that's equal to pi, isn't it? So that was kind of neat. And I probably could have died because I was thinking about evaluating an integral when I should have been driving. A clever play on the part of bumper stickers. Okie dokie. So this here is going to be a useful result. So we have already seen that 1 over x squared, integrated from 1 to infinity, converges, but 1 over x diverges. So we already know that when p is equal to 1, this diverges, but when p is equal to 2, it converges. So for what values of p is this thing going to converge? For what values of p is it not going to converge? Where is the transition? So let's work this out. And this is going to be a result which is worth remembering because it's going to come up later in the course as well. So we can anti-differentiate this because this is just, yeah, so let's turn this into a limit. This is the limit as t goes to infinity of integral from 1 to t x to the negative p. So we are assuming that p can take on any real number value. Okay, so within reason, we can use the power rule here. So this becomes x to the minus p plus 1 over minus p plus 1. And this is going to work as long as this denominator is not 0. So this is going to work as long as p is not equal to positive 1. Right? Because as we've already seen, when p is equal to positive 1, we get this, and we already know that that diverges. So actually, let me mention that first. So when p equals 1, from, what was it? Example 1, yeah. So when p is equal to 1, this diverges as in example 1. So let's assume that p is not equal to 1. So p is not equal to 1, which means that the power rule is perfectly valid. So no problem there. So this evaluates between 1 and t. So if we plug in t, we get... You know what? This negative is making me nervous, so let me put it on the bottom instead. Yeah, like so. So if I want to put it on the bottom, that means I just have to reverse the sign of the exponent. And then minus p plus 1, that's the same as 1 minus p, like so. And we're plugging in t there. And if we plug in 1, yeah, so if we plug in 1, this exponent bit just becomes 1. So that's all we have. Okay. So now, as t goes to infinity, really the only question is what happens to this thing? What happens to t to the p minus 1? Well, if this dude on the bottom goes to infinity, then this whole thing is going to go to 0. If this dude on the bottom goes to 0, then this is all going to go to infinity. So it depends on what the sign of this power is. Because if this power is positive, then okay, we've got a reciprocal, and so the whole thing goes to 0. If this power is negative, then actually we have to flip it upside down, and then the whole thing explodes to positive infinity. So we've got cases. So this is going to... Okay, so what did I just say? So if the power is positive, then that means this becomes 1 over infinity, which is 0. If So if p minus 1 is strictly greater than 0, because if it's equal to 0, then it's just 1, and it's going to be 1 forever. In which case the limit will just be 1. So that's actually going to be another special case that we need to consider. So if p minus 1 is greater than 0, well, that's the same as saying that p is greater than 1, yeah? Okay, alternately, if this dude is negative, then this is actually a reciprocal, which means that it's going to explode to infinity. So that's going to be the opposite situation. And then if p is equal to 1, then we have t to the power 0, so then this whole thing, it just becomes the constant function at 1. Wait a minute. Well, wait. No, we already did that. No, we already did that. We already did p equals 1. Never mind. Yeah, that's not an option. Oh, come on. Well, whatever. It's going to look like crap, but there it is. So, as our final result, what do we conclude here? Well, if p is larger than 1, then this becomes 0, so we just get negative 1 over 1 minus p. And it diverges in all other cases. So yeah, this is a result that's worth hanging on to. Yeah, this all becomes 0, so negative, I'm going to distribute this negative down here to get 1 over p minus 1. I think that looks a little bit nicer. So that was the case if p was greater than 1. And this guy diverges otherwise. Right, so if p is less than 1, it diverges, because that means this chunk explodes to infinity. And if p is equal to 1, well, then we already know that this diverges, because we did that example already. Okay. Yeah, so this is worth hanging on to. In fact, I'm going to put this in a box. Yep. So that's a nice result to have. Okay. So those are improper integrals of type 1. So improper integrals of type 1 are ones where you have infinity in one of the limits of integration. And you just turn those into limits. You know, replace the infinity with a parameter, and then let that parameter tend toward infinity. Now, here's another situation which ordinary integrals are not equipped to deal with. So let's consider the integral from -1 to 1 of 1 over x squared. Well, if we just naively do this with the power rule gives us -1 over x. Evaluate that between 1 and -1, and we get -2. But hang on. You think about this for a second, and you realize this can't possibly be true. 1 over x squared is always positive, right? You square a number, it's positive. You reciprocate it, it's still positive. So the integral of this thing should also be positive, right? You're taking an area of a curve which lies above the x-axis. So that would be positive by definition. And yet, here we have somehow obtained a negative number. And we didn't make any mistakes. Didn't make any arithmetic mistakes, at least. So what's going on here? Well, the problem is that this function, 1 over x squared, is not continuous on this interval. Definite integrals are only guaranteed to exist if the function is continuous over the interval that you are integrating. But that is not the case with this dude. Indeed, this has a vertical asymptote at x equals 0. So this guy is discontinuous at x equals 0. So what we've done here just straight up isn't valid. We cannot integrate over asymptotes. So that was the problem. So what do? Well, we can do pretty much the exact same strategy that we did before. If a function has an asymptote at a particular value, or more generally just some discontinuity, so like here we're saying the function f is continuous, blah blah blah, but there's a discontinuity over here at b, well then all we need to do is replace this problematic point with a parameter, and then let that parameter approach the problem point. Okay? So figure out where the asymptote is, if it's at one of these limits, replace that with a parameter, and then let the parameter approach the asymptote. Same exact strategy as before, only instead of approaching infinity, now it's approaching, a point at which the function has an asymptote. Or some other such discontinuity. But for us, it's always going to be an asymptote. Same deal here. And same deal here. So if there is a discontinuity somewhere in between the limits, then we just split it into two pieces. So if there's a discontinuity at c, we break this up into the integral from a to c plus the integral from c to b. Yeah. Okay. So first off, what is wrong with this dude? Why is this being included in a section on improper integrals? Well, this dude has a vertical asymptote at x equals 2, right? Because when x is equal to 2, it's going to be dividing by 0. And, well, wouldn't you know it, that's one of the limits of integration. So this is improper. We're going to have to approach this guy via a limit. So this is an improper integral of type 2. So what do? Well, we just replace the problem point with a parameter, t, and then let t approach that parameter. Or I'm sorry, other way around. Let the parameter approach the problem point. And in this case, we will be approaching from the right. Okay, so what's going on here? How can we evaluate this? Well, I mean, we just hit it with the power rule, right? I mean, if u is equal to x minus 2, then du is equal to dx, so there's not going to be any change. So we can just do the power rule immediately. So this is x minus 2 to the negative 1/2. Add 1 and we get positive 1/2. Dividing by 1/2 is the same as multiplying by 2. So there we go. Evaluate between 5 and t. So 5 minus 2 is 3. Minus 2 root t. Minus 2, rather. Okay, so now what happens in the limit as t goes to 2? Well, put a 2 in here, this whole bit just becomes 0. So no problem at all. No problem at all. So indeed this limit exists. It converges. It converges to 2 root 3. Despite the fact that there was an asymptote. So we're just pushing right up against the asymptote, but we're not integrating over it. Right? If we were integrating over it, then we would have to split it into two pieces, and then see what happens. Okay. Determine whether this guy converges or diverges. So what is the problem here? Well, secant at 0 is fine. Because remember, secant is 1 over cosine, so cosine at 0 is 1, so 1 over 1 is 1. But at pi over 2, we're going to have a problem, because, yeah, we're going to have 1 over cosine at pi over 2. Cosine at pi over 2 is 0, so that's 1 over 0, so that explodes. So there's a vertical asymptote there. Alternately, just look at a graph of secant, and you will clearly see there's a vertical asymptote at pi over 2. So, we take the limit as t approaches the problem. In this case, we are approaching it from the left. That may or may not end up mattering, but, you know, it's important to make sure that we're getting the orientation correct. Integral from 0 to t, secant x dx. So, what is the antiderivative of secant? Well, that's one of those that you just have to look up, unless by some miracle you've actually memorized it. So this ends up being natural log secant plus tangent. Yeah, that's correct. Evaluate that between 0 and t. So let's see, if we plug in t, we get that. If we plug in 0, what am I doing? Sorry, my typing is really shameful. Secant at 0 is 1. Tangent at 0 is 0. Okay. And that's all inside the log. So now, what happens if we plug in pi over 2? Well, same problem, right? Secant explodes, so this is infinity. And in fact, it's even worse than that, because tangent at pi over 2 is also infinity. So, this is log at infinity, but, you know, the logarithm also explodes as its argument tends toward infinity. So, yeah, this whole thing just explodes. So, it diverges. So just to write a complete sentence, this improper integral diverges. Or is divergent. Okay, so what is the problem with this one? Well, this guy has a vertical asymptote at x equals 1, and wouldn't you know it, 1 is inside the interval that we're trying to integrate over. So the problem occurs because we are trying to integrate over an asymptote at x equals 1. So we're going to have to split this into two pieces. So this is the integral from 0 to 1 plus the integral from plus the integral from 1 to 3. Okay. So let's focus on the one on the right for now. Yeah, sure, why not? So the problem, you know what, let's do the one on the left. So the problem occurs at 1. That's the place where we are encountering problems. So we take the limit as t approaches 1 because the limit always has to be approaching the problem. Like so. What the heck is going on? Hang on. Whoa! Sorry. Okay, it's fine. I think I just hit some esoteric keyboard shortcut. My fat flailing fingers hit some esoteric keyboard shortcut, and suddenly a big window appeared in my screen, and it was like compiling a bunch of code. That was scary. I hope I don't have a virus. Well, moving on. Man, keyboard shortcuts are scary. You never quite know what you're gonna get. Anyway, antiderivative of this thing is just natural log. No! Sorry. Clipboard. Natural log x minus 1. Evaluate between 0 and t. If we plug in 0, we get -1. So it's a good thing I remembered to put these absolute values here, or else I would be out of luck, right? Because natural log of -1 just straight up doesn't exist. But because there's absolute values, this is natural log of 1, which is just 0. However, that's still not great, because here, plugging in t equals 1, we get natural log of 0, but natural log of 0 is -infinity. So, yeah, so much for that. So, it doesn't exist. It diverges. So the guy on the left diverges. And if the guy on the left diverges, then who cares what the guy on the right is doing? The whole thing is doomed to diverge in that case. Yep. There's no need. Although it's going to end up diverging as well, for the same exact reason. Okay. Evaluate the integral of natural log between 0 and 1. So, again, what is the problem? Well, the problem is at 0, because natural log is a vertical asymptote there. So, limit as t goes to 0, integral between t and 1, right? You replace the problem with the parameter. Natural log of x. Now I don't remember if we've actually ever done this one. I don't remember. You can do this with integration by parts. Yeah, let's go ahead and do that, because that's a good one to be able to do on your own, just in case you forget this thing. Yeah, so the trick here is that you let u equal log x, and then du is equal to 1 over x dx. So if u is equal to log x, then that means dv has to equal dx, which means that v equals x. So plugging all of that in, so uv, so that's x log x, evaluated between t and 1, minus integral v, which is x, du, which is 1 over x dx. Oh, well, how interesting. x and 1 over x, those guys cancel each other. So this actually works out perfectly. So plugging in 1, we got 1 times log 1, but log 1 is 0. Plugging in t, we get t log t minus, well, this is just the antiderivative of 1. So that's x evaluated at 1 and t. So that's 1 minus t, like so. So let's clean this up a little bit. So we have minus 1 plus t, that's this bit, minus t log t. So now as t goes to 0, this dude just goes to 0, this dude remains unchanged. And then t log t, well, log of 0 is negative infinity, right? So we're going to have another indeterminate form of the form 0 times infinity. But we've actually done this one already. We did this one in the previous section on L'Hopital's rule. So recall that the limit this limit is in fact 0 by L'Hopital. So see the section on L'Hopital's rule. I mean, it's just our standard trick where we rewrite it as a fraction and then apply L'Hopital's rule. So we end up getting that this turns to 0, this turns to 0, so we just get negative 1 at the end. So that's neat. Okay. So in all of these cases, we have needed to compute the antiderivative, right? We're still computing antiderivatives and then taking limits on top of that. So improper integrals don't really introduce too much that's new, at least not yet. Yeah, because it's just do an integral and then do a limit. Two things we're familiar with, now just pushed right next to each other. The thing is, though, this is actually overkill. There is a way. If we can compare it, if we can compare the integral that we've been given to another integral whose behavior is well known, then we might be able to conclude that an integral converges or diverges without having to actually compute the antiderivative. In general, this is actually the much more useful strategy, especially because in quote-unquote real life, a lot of the integrals that you will be coming across are going to be impossible to evaluate by hand. So if you want to just determine whether it converges or diverges, you're going to have to use some other technique, since computing the antiderivative is sort of too much to ask for in general. So here we got the comparison theorems. So suppose that f and g are continuous functions, and f is always larger than g. So f is bigger than g. And also they're all positive. This only works if everything is positive. Well, oh yeah, and x is greater than or equal to a. So, let me actually say this. So this is how it was written in the book. We can make this a little bit better. We can make this a little bit better. So really all that we need is for f to be greater than g and for these guys to both be positive eventually. It doesn't have to be the case over the entire integral. It just has to be the case eventually. So for x larger than b, for some b inside the interval. And the reason is because then we can just split the integral into two parts. We can split the integral into the part from a to b, which is finite, so it doesn't affect whether it converges or diverges, and then the only bit that really matters is the bit where these things hold true. Yeah, okay, so if integral of f is convergent, okay, and now the thing on the bottom is our b, right? Because it only matters eventually. This whole first bit can be thrown out entirely. Yeah. So if this bit converges, then this bit with the lower limit equal to a also converges. Similarly, yeah. Okay, so this is a much a more general way of doing it. So in other words, if the guy on the top converges, then the guy on the bottom also converges. If the guy on the bottom diverges, then the guy on the top also diverges. So think of it as being like f is a cap on the function g. So if f is well behaved, then g also has to be well behaved, because g is bounded beneath f. On the other hand, g is below f, so if g explodes, f also has to explode, because g is underneath it. So, you know, f rockets into the sky, being propelled by the function g, which is beneath it. So yeah, that's what I say here. If the top converges, the bottom converges. If the bottom diverges, So the real challenge here, then, is just to figure out what function you should compare your integrand to. Because it has to be a function 1, which satisfies this property eventually, and also that you know how to integrate. Okay, so first off, let's show that this dude is convergent. And this is a good example for us because this is an example of a function for which it is actually impossible to find an antiderivative. So the comparison theorem is sort of our only option with this guy. So let me do this. I claim that the dude that we were given is smaller than this for x greater than or equal to 1. Now, why am I doing this? Well, because this is a dude that I know how to integrate. If I just let u equal x squared, then this factor of x is going to get canceled out. So this is something that I can integrate. Furthermore, if I can find that the integral of this guy converges, then that means this guy also has to converge, because it's smaller. Now, it's not always going to be the case that this is larger than this, but it will be larger for x greater than or equal to 1. And that's all you need. You only need it to be eventually larger. So, indeed, this is true because if we are starting from the premise... Sorry, other way around. If we are starting from the premise that x is larger than 1, well, let's just multiply both sides of this inequality by e to the negative x squared. We can do that. And furthermore, this guy is always going to be positive, right? Because the output of an exponential function is always positive. And if you multiply an inequality by a positive number, the inequality stays the same. Contrast, if you multiply an inequality by a negative number, then that means the inequality has to flip. So on the left, we get e to the negative x squared. On the right, we get x e to the negative x squared. And well, there you go. That's exactly what I wanted to prove. So, if we can show that integral from 1 to infinity of x e to the negative x squared converges, it follows from the comparison theorem that the dude that we were given converges as well. So, let's go ahead and do that. So we have shifted the problem onto the question of whether this dude converges. And that's a much better question to have because, as I've already said, this is someone whose antiderivative we'll actually be able to compute. Okay, so let's turn this into a limit. Now, let us do a u substitution. So let u equal x squared so that du is equal to 2x dx. We need to deal with these bounds as well. So when x is equal to 1, u is equal to x squared, so that's also going to be 1. When x is equal to t, u is going to be t squared. So that's what the bounds of our integral are now. Instead of 1 to t, it's 1 to t squared. X e to the minus u. And then instead of dx, I put 1 over 2x du. So those x's cancel. We have a 1/2 that we can pull all the way out, not only out of the integral, but out of the limit as well. Integral from 1 to t squared of e to the negative u du. Okay, so now we can anti-differentiate this. This just becomes minus e to the minus u, evaluated between 1 and t squared. So now just plug in the bounds. Okie dokie. So what happens? Well, as t goes to infinity, this becomes e to the minus infinity. E to the minus infinity is 0. So this chunk all goes away. So we end up with e to the minus 1 over 2. Like so. So indeed, it converges. Yeah. So that's it. That's it. That's all we need to do. We have already established that if this dude converges, then the dude that we are interested in converges as well. So that's all there is to it. Notice, however, that this integral does not converge to 1 over 2e. We don't know what it converges to. I've said nothing about that. It is this second auxiliary integral that we're comparing it to that converges to 1 over te. But we don't know what this dude converges to. That we would have to do numerically. Because indeed, finding an antiderivative is actually impossible. Not sure why, but that's a well-known fact. Okay, so let's show that this dude is divergent. Divergent, not convergent. So, for the comparison theorem, we need to show that this guy is larger than an integral which is guaranteed to diverge. Well, that's actually not too hard. Yeah. Right? Right? Because e to the minus x is always positive. So 1 plus e to the minus x is larger than 1. And then just divide both sides by x, and that inequality is still true. Yeah? Make the numerator larger, and the whole fraction becomes larger. Now, why is this an effective comparison to make? Well, because we already know that the integral of 1 over x diverges. So that means, as you go from 1 to infinity. So that means this integral also has to diverge. Yep. So it immediately follows that this dude diverges as well. Because it's bigger. And you can't be bigger than infinity without also being infinity yourself. Yep. So that's all there is for that one. So this idea of comparing things is going to come back a bit later. So make sure that you understand why it is that I am making these comparisons. And why it is that these comparisons hold in the first place. Okay, so that's all for this one.